Right. Okay. A very good morning to all the attendees here, and I thank the organizers for giving us this opportunity to present our preliminary work on the development of a portable all-optical trapped ion clock. So this is a work under progress, and what I will try to do is I will try to briefly motivate you about the need for the development of such all-optical clocks, and hopefully present the scenarios where these instruments are applicable, and then try to give an overview of our initial activities in this domain, and give some future perspectives, opportunities, and challenges. So I also thank Professor Saurav Datta for the kind introduction, and with that, let us begin the discussion. So the title of my talk is rather long, and I thought that it is best to encompass the directions in which we are aiming for, both technologically and scientifically. So we have both a technological perspective, and we also have a physics perspective so far as this particular project is concerned. So for people who are attending from outside India, I come from an institute called the Indian Institute of Technology at Tirupati. This is a rather new institute. It came into existence in 2015, and I joined there as assistant professor in 2018 October. We got our lab just this year after all the infrastructural hiccups. So we have been sort of little bit tied up because of the infrastructural issues that we have been facing since the last 5 years, but hopefully the future now looks promising. So the plan of the talk is I'll try to give some introduction and motivation as to why we are engaging in this project. Then I'll try to give some background which necessitates the the development of such kind of portable all-optical trapped ion clocks. We are going to discuss a little bit on the methodology and the current status. And finally, I will try to end the discussion with some future directions, challenges, and opportunities. So just to briefly tell you, this is the location of IIT Tirupati. It's pretty close to Bangalore and Madras. It's about 220 kilometers from Bangalore and about 150 kilometers from Chennai. So this is my group. These two students are primarily working in this project, Rishabh and Vikrant. Rishabh presented a poster here on the high finesse optical cavity, and Vikrant is right now on a research internship to Professor Amar Bhuta's group at the University of Toronto. So this is the current scenario of clock projects in the country. I'm sorry if I have missed anyone, but I think I have included almost all the groups who are currently working in the domain of atomic clocks. These are different types. Some, yes. Oh, okay. I saw her webpage, and I thought she's working on quantum computing. Apologies to Ranjita. So I should have put your name there. Okay, great. Thanks for the correction. So, so as I mentioned, we have IIT Kanpur, then CSIR NPL, who has been the traditional player in this domain. Recently, SSPL, the DRDO lab, that has also started working in this area. SAC ISRO, they have built a space-grade portable atomic clock, which was recently launched in a satellite to be integrated in the NAVIC system. And then we have teams from RRCat Indore, RCI Hyderabad. Pune, incidentally, has two institutes, both at IISER Pune and IUCAA Pune. So Professor Subhadeep is already here, and Professor Umakant Rapol's group also at IISER Pune working on these kind of clocks. Then there is Professor Sadiq Rangwala's team at RRI Bengaluru, and there's a small group at LIOS ISRO, which is looking at CPT-based clocks. Then in our group also at IIT Tirupati, which is trying to develop this kind of technology for both the practical applications as well as the physics opportunities that are involved with these kind of projects. So what is PNT, right? Because this is what the whole gamut of activities related to atomic clocks connect to. So PNT stands for positioning, navigation, and timing. So when we talk about positioning, it's the ability to accurately or precisely determine one's location and orientation on a two-dimensional, or let's say a three-dimensional surface reference to a certain standard geodetic system. Okay. What about navigation? Of course, that we understand. We want to travel from one point to another, let's say on the surface of the Earth or in space, and that again connects to the corrections to course, orientation, and speed to attain a certain desired position on the target trajectory. Timing. So this is the ability to maintain accurate and precise time from standard, from a standard coordinate universal time, or the UTC. So anywhere in the world, and with user-defined timelines and parameters. So timing also includes timing transfer. And so when you use PNT with combination of map data and let's say other information, weather or traffic, the result is a very popular and recognizable service, which is the modern navigation system, better known as GPS. So in fact, all of us, we have GPS installed in our mobile phones, so we can access the GPS signal and we can, figure out a trajectory when we want to go from one point to another. So even though the GPS and GNSS are typically thought of as positioning and navigation systems, they are in fundamentally reality precision timing systems, right? So the position and time at a receiver are determined by the transit time traveling at the speed of light from multiple satellites. So what we have is a constellation of satellites around the Earth, and depending on the various options, you can have GLONASS, you can have GPS, you can have Baidu, right? These are all, and of course, India's own NAVIC is supposed to come in very soon. And these all rely on a constellation of satellites that are orbiting the Earth. These satellites carry onboard atomic clocks through which we can map the position and location of the user on the surface of the Earth. So the importance of the precision timing devices is not restricted to navigation and positioning. Because if you look at current day technologies related to the mobile or internet communication, we started with 2G, then 3G, subsequently 4G came, now 6G is there, and eventually the technology is going to increase by leaps and bounds, which requires enormous amounts of data transfer. So how do you synchronize this huge data transfer so that you have a seamless network and seamless connectivity to various users on the internet, right? So again, for that, you need precision timing devices, and this is where atomic clocks play a very critical role. So timing from atomic clocks is now an integral part of data center operations. So we have a lot of service that is generated from the cloud. So you have AWS, you have Microsoft Cloud, you have so many other players, and all of these data centers, they have a clock connected to the data center so that there is a very coordinated and synchronized data transfer from users across the globe. So this is the standard architecture of PNT, right? So you have the base stations which are creating the networks, and then you have several users. So you are getting the signals from different types of position systems like GPS. You can have NAVIC right here, that is also mentioned here. And then you have these cell phone networks or other networks that connect to different users, right? So this is the standard architecture. Now, what happens is that the GPS signal, which we so reliably use in our daily lives, that itself is a very susceptible source, okay, so that it can, somebody can actually, trigger issues with the GPS signal and try to confuse the user, right? So the ubiquity of the GPS signal as the primary source of the PNT information, although it provides a free service for navigation, timing, and precision timing, okay, the over-reliance on GPS itself is a problem for us, right? So there are situations where people or natural events have hampered the access to GPS signals, and that has led to complete disruption of different communication, or let's say, the navigational aspects connected to airlines or freight, which is like on the sea. Okay, and the threats to GPS, okay, can be multiple. It can be ground, air, or space based, and it can be electronic also. Nowadays, you have these electronic jammers where an adversary can create problems for you, okay, and completely block the GPS signal access. So then there are insider vulnerabilities. Okay, you can have network receivers that present cyber attack challenges. So the threat has now expanded from a nation state to an informed hobbyist, right? So there are potentially different ways in which the GPS signal gets affected. So you can have unintentional interference that is coming from radio frequency, or somebody is testing, then there's ionospheric, okay, solar spectrum, okay, solar winds, spectrum congestion. All these are unintentional, but then there are also intentional blocking of GPS signals connected, and some of these can be categorized as jamming, okay, spoofing, okay, then there's meconning, okay, and system damage. And over and above all this is human factors, right? Because people who are potential users, they may not be aware of how to handle that technology, right? So there can be an over-reliance with that. Also, there is something like, the lack of knowledge and training on how you use these things. So what are the factors affecting the GPS signal? So you have, first of all, the GPS signal is actually very low powered, okay? It's a very well-known signal frequency. It has a well-known signal structure. There is a lot of spectrum competition, and the worldwide military applications drive a GPS disruption industry. Why? Because if you have an enemy state, that fellow will try to block your operational surveillance, okay, by blocking this GPS signals. So these jamming techniques are very well known, and these devices, okay, 20 years ago used to cost a lot of money, but now you can get GPS jammers which can function through your USB port, okay, at the cost of only 5 or 6 euros. So here I present an overview of the critical GNSS applications and the PNT dependence on these applications. So you have potential users like transport, communication, finance, critical infrastructures like traffic lights, energy, okay? Then of course there's government users and then defense users. And what you realize is that all these domains in some way or the other, they are reliant on position information or timing information, or both timing and position depending on the application. So the major threats to GPS, as I mentioned, was jamming. So what is jamming? Basically, it is to block the physical GPS signal itself in noise, okay? Spoofing is to mimic the signal, okay? And meconning is actually you are releasing the true signal, but from a different place, right? So as you can see, okay, from the potential, the technology improvement in GPS jammers, the first commercial GPS simulator came in '89, but then as of 2018, a simple USB 3 GPS adapter, okay, can cost as low as 5 euros, and it can cause a lot of disruption in the potential user. So the spoofers, jammers, repeaters, and meconers, these are very critical when you come to defense or space applications, because the navigation of military vehicles, okay, whether it is land-based or air-based, okay, or if you're trying to launch a particular vessel in the air, all these are critically dependent on the GPS navigation, and there is always a consistent threat from adversaries, and they create all these kind of problems for the users in the nation. So this is a cartoon which shows that how the target ship, okay, is led in a different course by a spoofing GPS signal. So in the context of the PNT architecture, what are the major gap areas? So this is related to jamming and spoofing. It's related to high accuracy with integrity. There are less availability of the current maps, okay? Then there is a problem with the timely notification of misleading information. And then you have noticed perhaps that if you are in a congested city, urban environment, okay, sometimes you see a loss of the GPS signal. So what is the road ahead? The road ahead is to actually build a resilient PNT system. So the resilient PNT system means that we want to have GPS level accuracy without relying on GPS, right? So for that, there are certain technologies that come in very useful. One is, of course, optical clocks. The other is inertial sensors like, gradiometers and stuff like that. Then you have external measurements like precision time, transfer or jam resistant ranging, and a fusion of all these three technologies would lead to a resilient PNT system, okay? So how do we use portable atomic clocks in our regular life, right? So many real world applications, okay, or devices, they rely on 1 microsecond synchronization. So for instance, if you look at power grids or communication networks, or for instance, you are having this trading in the stock markets, right? So they rely on this 1 microsecond synchronization. And usually this is achieved via the GPS signal. So the GPS signal can be intermittent, noise you're jammed, right? And so what you need is a reliable holdover clock or a timing reference, right? So typically, if you look at oven controlled crystal oscillators, they have a holdover time for 1 microsecond duration of several hours. The CSAC, okay, which was developed under the aegis of the NIST at USA, that can hold this 1 microsecond synchronization for about 8 hours, and optical atomic clocks are expected to hold 1 microsecond synchronization for greater than 50 hours. So the aim is to develop a technology that is fieldable, which can operate outside the lab. It has low size, weight, and power, right? So that is the motivation. So I think we have seen a bunch of presentations and talks on the background of optical atomic clocks. Yesterday itself, Ranjita gave a beautiful discussion on the lutetium optical clock. So just to briefly, recuperate the basics of the optical clock or how a clock works. So we need a system with periodic behavior. It should cycle at some constant frequency. And what we need is to count the cycles to produce a time interval and then agree on the origin of time to generate a time scale. So this is the essence of a clock. So when we talk about atomic clocks, what we need is we need a reference, okay, that is the atom, right? And here we are talking about trapping a calcium ion for this purpose. We need an oscillator, which is this laser, which is going to drive the transition. And then we need a mechanism to count the frequency, right? So for that, we need the frequency comb. So this diagram, this block diagram, gives a good overview of the elements of a clock, right? So you have the oscillator, you have the reference, and you have the counter. And so from the counter, you can get the user output. Okay, so the typical user output is a 10 megahertz signal, okay, and that is what we need. So the optical comb, the optical frequency comb comes in very handy because it can translate this measurement in the optical domain down to the radio frequency domain at few tens of megahertz. So what is the advantage of working with optical clocks? Well, we have the conventional microwave clocks, okay, the cesium fountain clock, okay. Compared to that, okay, what we see is that given the clock instability, okay, this quantity delta nu by nu zero, okay, which is the inverse of the quality factor, that plays a significant role, and it tells us that we can improve on the instability if we go from the microwave to the optical domain. So the optical clocks rely on the principle of forbidden transitions in atoms on ions. They have a natural line width of about a hertz or less. The frequencies are in the terahertz range, and the quality factor is on the terahertz range or over higher. Okay, so the potential advantage of moving from the microwave to the optical domain is established, and so there is a growing impetus in the community to develop portable clock technologies based on these optical transitions. So here I show the entire gamut of activities that are going to be influenced by the development of such portable atomic clocks. And you can see we not only have the PNT applications, but we also have applications related to geodesy, we have applications related to fundamental physics, we have applications related to the origin of the universe that can be studied through such precision measurements. So here this is a brief motivation on the commercial aspects of developing such a technology. So the global atomic clocks market is expected to reach about 320 million by 2027. So when we are looking at this optical atomic clocks, as I mentioned, for the project that we are trying to do at IIT Tirupati, we are using a trapped ion. Okay, of course, one can also use neutral atoms. For instance, Professor Umakant Rapol at IISER Pune, he is looking at using strontium atoms, loading them in optical lattice, and trying to do a clock measurement with them. For us, of course, we are using this trapped ions, and this is based on forbidden transitions in single trapped ions. So we are looking at, for our project, we're looking at calcium ions. The advantage is it gives us long interrogation times, and because we are trapping a single ion in a very well isolated environment, there is very minimal effects on perturbation, issues connected to the measurement. So you don't have a first order Doppler shift, you have a minimal second order Doppler shift, and this can be removed through the choosing of the appropriate frequency, trying to drive the trap. So this is known as the magic RF frequency. Then the field perturbations are minimized at the trap center. If you design your trap parameters, if you design the trap well, you can minimize the trap parameters, the perturbations at the trap center. And since you are working in this enclosed environment inside the vacuum chamber, the background collision rate is pretty low. So the environment is very conducive to development of such portable atomic clocks. So why do we choose calcium? Okay, out of all these elements, okay, what motivates us to choose calcium? So if you look at the energy level diagram of the 40 Ca plus ion, you will see that there is no hyperfine structure, right? And so it is a relatively simple energy level structure to access. There is availability of cheap diode lasers and laser systems for photoionization, cooling, and clock transitions. Then the calcium atom itself has multiple isotopes. So if one wants to explore physics beyond the standard model, there is an opportunity to explore that physics. Finally, because of this unique magic RF operated frequency trap, okay, it mutually cancels the micromotion induced scalar Stark shift and the second order Doppler shift. This was also exhibited or demonstrated by the NRC team in Canada. Okay, so they have shown that. So these are the isotopes of calcium with their natural abundances specified, and the different transitions in the isotopes are also labeled. Okay, so the references from which this data has been compiled are given here, right? So what it shows us that given the possible isotopes, we can see the whole gamut of isotopes. If one wishes to make very precise frequency measurements, there is a potential opportunity to connect to the studying of the new physics beyond the standard model. So for instance, this is a plot from the Aarhus team. Okay, they measured this data in 2020 and published it, and you can see the new physics coupling constant, which is given in the y-axis, versus the projected mass of the boson, right? And Dima, who is in the audience, okay, he was one of the first authors to propose this idea, and I think this paper by Berengut et al. This is Dima's paper from 2018, and in 2020, the group of Professor Michael Drewsen at Aarhus University, they measured the different transitions across calcium isotopes and produced this result. So our hope is to develop a transportable all-optical atomic clock where we can put everything on this racks, which can be transported to different place if needed. So we are trying to transition the experiment from the lab environment to a field-oriented, environment. So we have the clock laser, the comb, the laser systems, the physics package, everything mounted on these racks, which can be transported. So probably we are aiming for 3 racks. Probably around my height, yeah. So we are working closely with the group of Professor Subhadeep Dey and Professor Adi Rangwala at RRI. In fact, they have been developing this precision iron trap. And when we kind of came to know that they were developing this, we said, okay, we would like to partner with you on this project and be a potential user for the trap they have designed. So what you see here is the design that has been developed by Professor Subhadeep Dey and Professor Sadiq Rangwala at RRI. And this trap is now being machined at CMTI Bengaluru. What I understand is that the initial fabrication results have been promising, and the testing and characterization of the trap surface quality is under progress at RRI. So apart from the trap, because as we mentioned that we want this 19-inch rack architecture, so we have to develop these compact laser systems, and we are talking to potential startups who can help us develop this technology. No, so they will do the laser development themselves. So we will provide them the design, and they will help us machine everything and integrate. That is the RRI startup, yes. So this is a collaborative project. So we asked them to build the system for us. We test it, and then if the technology is mature enough and we are happy, then right. So for this, actually, the entire design needs to be changed so that we can fit in the fiber coupler, isolator, the vapor cell, everything for spectrum. So, diode, of course, is imported. Yeah, definitely. Yeah. We don't have. Yes. So new ECDL designs which can perform at the level of what we need. In fact, nowadays, I have seen there are acoustic modulators which are fiber based, right? So the technology is progressing quite rapidly, and we are hoping that we should be able to come up with these kind of compact systems where everything is integrated, and we can use that. The potential user just has to turn the knob, and everything will be in place in the right frequency. So we did a simulation of the trapping parameters in SIMION, and you can see here the trap frequency is this magic frequency of for the calcium ion 40 Ca plus 24.8 megahertz. We did the simulation for that, and we found the trajectories of the X and Y and the Z to be consistent. You can see the micromotion here, okay? And then this is the power spectrum, which shows that it's a very clean spectrum, power spectrum, okay? And it gives us a reasonable separation of the axial and the radial secular frequencies. We are also working on developing our own high finesse optical cavity. So Rishabh, who is here, he is working on this project, and we have, to freeze the initial design parameters about the optical cavity, and we are trying to simulate these, the performance of this optical cavity in this finite element analysis modules. Okay, that is the work that is going on. So we are looking at No, no, not now, not now. That's a work under progress. So we hope that this will be completed in the next few months. So that is, the preliminary design and the sensitivity limits that we can attain through this kind of this kind of optical cavity, that we can hopefully come up with a number in the next few months. This one, yes, this one will be in the clock laser. Yes, yes, yes. Yes, we have kept it horizontal. Yes, yes. So correct. So the vertical orientation that we thought, okay, yes, that's of course a possibility. But we thought that given the challenges, if we are thinking about putting this in a transportable system, the vertical orientation might get disturbed more easily compared to the horizontal. So that is the reason, this is out of simply practical considerations that we thought we'll put it in the horizontal axis. Okay, so for instance, you might be aware about this rectangular cuboid cavity from NPL UK, which is a rather short cavity, but that has shown exceptional performance in terms of the frequency stability. So that kind of motivated us to go in this direction.
Arijit,
Yeah.
What is the material you use for your cavity?
So this one is ULE.
Okay, and the glasses are like you are going to assemble it here, or what is the plan of?
No, so we are going to talk to the coating teams outside India, because in India we don't have the technology to coat mirrors at the level we want to achieve this finish. So we have to talk to people outside. So once the design is frozen and we are sure of the performance, like what Subhadeep was asking just now, once we are sure of that, we will approach the coating people outside India.
Assembling and that you wanted to do here?
Yes, that is what we wanted to do it here. Assembly and all, that's what we wanted to do. Yeah.
Who is the expert to do that kind of work here in India?
Well, we don't have the expertise. We have to develop that, right? I mean, we don't have, I don't think there is any player in the market who can do it for us. We have to try and evolve this technology on our own.
That's the plan?
That is the
okay,
plan.
that's nice. Huh?
Yeah, it's actually, it should be polyurethane actually, rather than plastic. So this is one of the most critical elements in this project. The stability of this cavity and the performance of the cavity is going to determine how the final stability of the clock is going to be. So we are trying to also come up with these platforms which can create a significant damping, so that if you are moving the apparatus even by a small amount, that vibrations damp out in a very short time. So that is no, I don't want to develop. I don't want to, but at least we need to tell the parameters. Yes. So this is also work under progress.
Procuring in-house. Yeah. This one also you're procuring from Indian company?
This one, no, I don't think in India we can get these piezo actuated platforms. Probably these are.
But there was some advertisement for the table, the vibration isolator somewhere from Chennai.
You mean in my presentation?
No, I have seen some people are doing vibration isolation tables in Chennai. Are they able to do this kind of job?
I am doubtful actually. I'm quite skeptical about their abilities. Okay. I mean, so we do have companies in India which make vibration isolation tables, but probably not active vibration isolation tables. What we need is an active vibration isolation table. What they make is a passive vibration isolation table, right? So there's a difference. This platform will be piezo actuated, like there's a feedback loop going constantly on the platform, so that any kind of vibration gets damped out within like a millisecond or so. That kind of time.
So you
can we let him finish the talk, because he's running out of time, and then
Yeah, okay. This is a vacuum chamber design that we are trying to develop in-house. This is again very closely inspired by the NPL UK team. So we are motivated by their design in coming up with a compact form factor for the entire vacuum assembly. So we are trying to make it as compact as possible, and at the same time giving the maximum exposure to the imaging. Right, so we want to image this single round. So we want to have a very high efficiency, a diffraction limited imaging system. So we wanted to give this vacuum chamber a design that it becomes very compact. At the same time, it gives us maximum freedom in terms of optical access and imaging. So this is the top view once again of the same chamber. So I'm very close to ending. So this is the current status. We have 2 PhD students who are working on this project. They're working on the 2 important aspects of the project, one related to the development of the chamber and the imaging system. And Rishabh is working on developing the optical cavity. We are, of course, collaborating with the groups of Professor Subhadeep Dey and Professor Sadiq Rangwala at RRI. And we're trying to look at the precision ion trap development. Vikrant has recently been to Canada on the MITEX GlobalLink scholarship to Professor Amar Bhuta's group to gain valuable experience on this, this project. And then we have an active collaboration with numerous national and international research groups in this area. And we have also identified key startups to foster innovation and indigenous development of technical subsystems relevant for the project. So this is the acknowledgement slide. Of course, I'm acknowledging Sadiq and Subhadeep, Amar, who has been a close friend, and then the Center for AMO Sciences and Technologies, KMOST, for the initial seed funding for this project, MITEX and SICI, IIT Tirupati, and of course, the team of students who have been working very hard to get this project to fruitfulness. Okay. Thank you. Yeah, so if there are any questions that, yeah, sure.
This trap design is very nice. It's very open. So do you think there are any limitations to applying higher frequencies to it? For example, gigahertz.
Sorry, I didn't get your question. Can you please?
This ion trap is extremely nice open designs.
Yes.
From every direction.
Right.
Do you think there are any limitations on applying higher frequencies to it? For example, gigahertz.
Okay, this is an interesting question. We have not thought about this. I don't know per se if there's any limitation. I mean, maybe technological limitation is there, but physics-wise, I don't see.
For 1 gigahertz, you have to apply like
that's what I said.
1,000 kilovolts.
That's what I said. Technological limitation.
In your transparency 30, you gave figures for the revenue of optical clocks in 2022 or so. Where do these figures come from, and what does they mean? Okay, so I think the market potential for these atomic clocks that I showed the figure, that comes from a survey of a particular business think tank. So they did this survey and they came up with that number of the growth of the commercial aspects of portable atomic clock technology. So that is the number coming from their report. No, it's not very much. Yes, but the fine print is that the clock technology is closely related to the GPS industry. So potentially, the growth of the GPS industry is going to impact the growth of the portable clock technologies as well.
What is the accuracy of this portable clock you were expecting at the end?
So of course, this is a work in progress, and we have to go in phases. So our initial estimates is at the 10-15 level, and then probably you might be aware of the group of Professor Kailin Gao at China, where they have actually now reached 10-18 levels with calcium ion.
Okay, if there are no other questions, let's thank Arijit once more.